The objective of this project was to use neural networks to classify user sketches and generate their visual counterparts. So the fun part of it was teaching a model how to draw. For the data, I used the data from Google's Quick Draw dataset. It is a large dataset with millions of 28 by 28 grayscale sketches drawn by people all around the world, which also means that it has all kind of scattered data. So all the data might not be correct, like a sketch of cat could be a sketch of a bird. For this project, I only chose 10 subclasses, which had around 50,000 number of samples. I chose classes like flower, hat, bicycle, few of them. For the classification part, I went with a CNN model with several convolutional layer, max pooling, and batch normalization. For training settings, I used Atom Optimizer, sparse categorical cross entropy, and I used early stopping and reduced LRM2. For the processing part, I used data augmentation because I think the user all around the world are different, and the dataset consists of random, rotated, or different height and width, or just zoomed in out kind of pictures, which actually helped my accuracy hike up after the augmentation. So I got an accuracy of 95 from 92. This was the front end I built to see how my model works. So it was pretty good while it was predicting candles and hat or stars and trees, but it did have problems or hard time where it mixed up flowers and trees, which actually makes sense visually because some sketches are really ambiguous. Same goes for hat versus tree, or even star versus face, and I think that's because some of the stars had faces drawn inside it and it looked like a face. So these weren't actually errors, but they reflect the fuzzy nature of hand-drawn data. This confusion matrix shows us the differences between each classes. That was my F1 score. For the next part, I built a conditional variational autoencoder. This compressed the sketches into a compact, smooth lattice space, and it learned how to reconstruct or generate a new image, either based on previous image input or a label. So for this, I start with a sketch and its label. I merge them with the image, and it passes through 3 convolution layers to extract features. Finally, it gives us 2 vectors, that is a mean and a log variance, which represents a distribution in lattice space. So instead of using mu directly, I apply the reparameterization trick, which gives me a sampled latent vector that captures both image structure and label. And in the decoder part, the latent vector is again combined with the label, and then it passes through the layers and it upsamples to give me back a 28 by 28 sketch. So the output is either a reconstruction or a new sample from that label class. For the loss function, I go with the combination of reconstruction loss and Kiel divergence loss. So it shows me how far the lattice space drifts away from the normal. On generating the images, the top row is the original image and the below one is a reconstructed image. The image in here, you'll notice that some outputs like face and star are a little blurry, which is a known limitation of VEs using pixel-wise losses. But for other classes like fish or a tree, the reconstructions are good. The next example is a decoder generating a sketch purely from a label, so without seeing an image. This part still needs improvement and the results aren't always clear, but I believe that switching from an image input to a stroke-based vector data could significantly boost the quality. Overall, this project helped me explore both a discriminative model for classification and generative model for creation, so I had fun building it. Thank you.